today we're going to go ahead and label our notes for the lesson that we have, Covalent Bonds 3. And this is Lewis structures. Now we've already done Lewis structures for single elements. And so hopefully you're thinking, oh yeah, I remember how to do that. Did you get out your notes? Are you paying attention? Okay, so when we did this earlier, we had two rules. The first rule was find the group number or the valence electrons. So we'll go ahead and review those. Okay, so we had taken notes on a periodic table last semester, and we talked about how the group number for the main group is the number of valence electrons. So this first column has 1, 2, skip the transition metals, and then you continue counting. 3, 4, 5, 6, 7, 8. And that is the valence electrons is what's at the top. So then the second rule, or the second instruction for doing Lewis structures for single elements was to seat the electrons. We talked about how when you place valence electrons, you pretend like you have a table. You have this table analogy, and there are two seats on each side of the table. But everybody likes their elbow room. So when you seat your electrons, you seat one electron on each side, and then you double up if you have to. So you want to keep that in mind as we'll do some examples of those. Alright, so let's look at a couple of ones that we probably remember. Hydrogen. Alright, so the first thing, find the group number or the valence electrons. Find hydrogen on the periodic table. It has one valence electron, so then I'm going to seat that one valence electron at the table. Simple, right? Okay, so we're adding to this a little bit. We want to think about what did hydrogen bring to the table. Hydrogen brought one valence electron. When we go to make our covalent bonds, we're going to have to use that in order to place them. All right? Let's look at oxygen. Okay, so if we find oxygen on the periodic table, we go up to the group number, and it is 6, so it has 6 valence electrons. So we'll seat those electrons. 1, 2, 3, 4, 5, 6. Okay, so oxygen brought 6 valence electrons to the table. Alright, give me a thumbs up if that makes sense and you remember that. Okay. Alright. So I want to point out something right here. You already know part of this, but we're going to put a little more to it, a little name to it. What did we call these electrons here before? We called these guys lonely electrons. Why are they lonely electrons? They don't have a buddy, right? What do these lonely electrons do? They make bonds. So if they're making bonds, then in a covalent bond, they are going to be shared with another atom. Right? So if these are the electrons that are going to be shared, that are going to be doing bonding, and this is kind of a Mr. Obvious statement, but these electrons over here are unshared. Electron pairs. So unshared electron pairs. Alright, let's let that sink in for a second. What's true about electrons. Any thoughts? Electrons fly around. Electrons are really little. Electrons, what charge do electrons have? Electrons are negative. If these unshared electrons are negative, and this lonely electron is negative, are they going to attract to each other? Or repel from each other? Repel, because they're the like charges. So we're going to make kind of a note of that. Electrons repel each other. This is a really important but really simple concept that you kind of need to keep in the forefront of your mind as we start to talk about geometries. Because these unshared pairs are going to push everything away a lot more strongly than the shared ones, than the shared electrons. So we'll come back to that when we talk about geometries in just a little while, but let's continue our Lewis structures conversation. Okay, so we kind of remember how to do Lewis structures for single elements. Let's look at some compounds, okay? So we know that hydrogen is normally a diatomic element. It likes to have a buddy. So if we are going to go to make, to draw this Lewis structure as a bond, the first thing we have to think about is, like we did up here, what are the Lewis structures? And we've kind of done that before. Okay. And then we're just going to bond those lonely electrons. So let's kind of digest this out for just a little bit. First of all, how many energy levels does hydrogen have? So we look at our periodic table, and hydrogen is in the first period, so it just has one energy level. How many electrons can fit in the first energy level? 2. Okay. So if we look at this Lewis structure, the electron that this hydrogen atom brought to the table and the electron that this hydrogen brought to the table can both fly around this first hydrogen atom. So it is being shared. Both of these can fly around. This guy feels like his first energy level is full. He's happy. This hydrogen has both of these same electrons that is being shared. Both of them can fly around this atom. This atom feels like its energy level is full, so it's satisfied. Right. Even though we just have 2 electrons, by sharing them, we have plenty to satisfy both of those atoms. So let's talk about those valence electrons just a little bit more. This is a very simple example. We're going to do some more complicated ones here in a second, and as we go along. But let's look at this table. How many atoms of hydrogen did we have? 2. How many valence electrons did each atom bring to the table? 1. So 2 times 1 is 2 total valence electrons. Alright, so let's take note of what we actually wrote there. First of all, we write the type of the atom. Then we write the number of that type of atom, so how many. And then the number of valence electrons from each. So in this case, we had 2 valence electrons total. Give me a thumbs up if that makes sense, everything we did. Okay, alright. So this is kind of showing your work. Like I said, this is a very simple example, but we're going to get a little more complicated as we do some more examples. Alright, let's look at NH3. Okay, so this one isn't quite as simple. We still have hydrogen, but then we have this nitrogen here. So let's think about, we have nitrogen. How many nitrogen atoms do we have? Just one. How many valence electrons is nitrogen going to bring to the table? Okay, look at our periodic table. Nitrogen is going to bring 5 valence electrons. So that's 5 to start with. Hydrogen. How many hydrogen atoms do I have? 3. How many valence electrons is hydrogen going to bring to the table? You have to go back and look if you need to. Hydrogen's going to bring 1 valence electron. We should probably have hydrogen almost memorized by now. So how many total valence electrons are in this molecule? Five plus 3 is 8. So that gives us the total valence electrons that we're going to work with this molecule. Alright, so when we go to draw the Lewis structure for this one, we got to think about, how do I want to lay this on my paper? First, nitrogen's going to be the central atom because it's the only one different. All of the others are the same, so they're going to kind of go around the outside because atoms tend to like symmetry. So let's put nitrogen here. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. So we seeded our electrons. And then we can see that there are 3 lonely electrons here. We conveniently have 3 hydrogens in this formula. So hydrogen, hydrogen, hydrogen. Right. So we're going to make our bonds here. And you can already, we haven't talked about shapes and geometries yet, but you can already kind of see that this one, the shape of this molecule, because of the way we've drawn it. Notice, what did we call this right here? Unshared electron pairs. So when we talked earlier about the unshared electron pairs, we said that those electrons are going to repel. They're going to push away everybody. So this unshared pair is going to push down on these hydrogens, and so you're actually going to have a structure that kind of looks like this, with that at the very top. Okay. So for right now, this is where we want to make sure we can get to really easily. And I did, give me a thumbs up if that makes sense, and everything we've done is like, yep, got that. Alright, good. Because that was kind of the review part. Right now I'd like to look at an exception to the octet rule. Because most of the time, like if we look at this nitrogen, we're going to have 8 electrons surrounding the nitrogen. Most of the time we're trying to fill an octet. So let's look at nitrogen. We have 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen is happy. It's got its octet full. And that's mostly what we're looking for. But I want to look at an exception to that. So we're going to look at this SO2. So let's digest it just like we did earlier. So sulfur, and we have oxygen. How many atoms of sulfur do we have? Just 1. How many atoms of oxygen do we have? 2. Okay, so then we need to look for their valence electrons. Well, conveniently, they're right there together. Oxygen has 6 valence electrons. Sulfur has 6 valence electrons. So let's 1 times 6 is 6. 2 times 6 is 12. So we're going to have 18 total valence electrons. Right? So just like we said up here, if there's one all by itself, it's usually going to be the one in the middle. So we have a sulfur. And I'm going to say 1, 2, 3, 4, 5, 6. It doesn't matter how you spread out your electrons, but I did it this way because I knew I was going to have one thing on each side. So it just makes my drawing easier if I put my lonely electrons where I think I'm going to draw my other atoms. So oxygen, 1, 2, 3, 4, 5, 6. And oxygen, 1, 2, 3, 4, 5, 6. So once again, you notice on my oxygens, I left my lonely electrons close to what I was going to be bonding with. Okay. So then we can kind of identify, there's our lonelies for oxygen. Here's our lonelies for sulfur. We kind of already pointed those out. And, I mean, it seems like, alright, we're going to connect the lonely electrons. Alright. I'm going to use a pencil on this one because our natural first instinct would probably be to just draw a straight line here and connect them. But what you create in that is that you would have this triangle. And sulfur has 2 sets of unshared pairs, and oxygen has 2 sets of unshared pairs. And what happens is there's too much stress on this triangle structure. The angles are too tight together, and so the pressure from these unshared electron pairs pushing, repelling the other electrons causes this to break apart. So that triangle structure doesn't work. Okay, and you probably maybe wouldn't have known that if we didn't kind of talk about these unshared electron pairs being kind of bullies. They kind of push everybody away. So you're thinking, well, what am I going to do then? Sulfur is an exception to the octet rule. So let's write that, and then we'll talk about why. Sulfur is not the only exception, but it is an exception. So let's look at it. I'm going to go way back to electron configuration. The electron configuration for sulfur was 1s2, 2s2, 2p6, 3s2, 3p4. Okay? And that gives us the 16 that we need for sulfur. So we know that p's can hold 6. So right here we have 2 spaces. That is these spaces right here, where those lonely electrons ended up being. But let's consider 1s has 1 orbital, 2s has 2. What's true about the third energy level? There is a 3d in the third energy level. So technically, sulfur can fill into the 3d if it needs to, because that's the same energy level. Okay. So that is how that's what we're gonna look at next, is these electrons right here are going to separate and make a bond here and make a bond here. Right? So now, let's look at sulfur. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So sulfur technically has 10 electrons around it in its outer shell, but it can handle it because it has this space here to expand into. Now, it doesn't always stay like this. Okay, and we'll talk about this idea later when we talk about resonance next week. But this concept right here is important for you to understand that there are exceptions to the octet rule. And so when you look at that, look at sulfur on the periodic table. Sulfur is here in the 3 P's. It could expand to the 3 D's. So everything in this row could do that. Everything in this row, the 4P, could expand to the 4D. Okay, so everything down here could be an exception if it needed to. Also the area we don't really deal with very much. You just needed to know that there are exceptions. Alright, so we're gonna kind of try to get the whole page of notes on there real quick. And then